There are a number of different types of enthalpies that you may encounter. In this case, there's typically a subscript after the delta H, which is indicating the type of reaction that we're talking about. For example, if you have a heat of vaporization or an enthalpy of vaporization, we're talking about the phase change of a substance going from the liquid phase to the gas phase. Alternatively, you could have the heat of fusion or the enthalpy of fusion associated with the liquid forming the solid, or vice versa, solid going to the liquid. So that's essentially melting. And you can also have the enthalpy of reaction, which is associated with any chemical process where we're converting reactants into products. We can also have a specific type of reaction, an enthalpy of reaction, where it's a combustion reaction. So there are delta H's of combustion. And then finally, we also have the enthalpy of formation, which is a specific reaction in which you are making a compound from its elements and forming 1 mole of the substance. If we discuss the concept of standard enthalpies, the symbol that we would use would be a delta H with a superscript of 0 just to the right of the H. This is a enthalpy that's been measured under standard conditions. So in this case, we're talking about the heat of combustion associated with some process. And so as an example, we could have the enthalpy of combustion when we were to do the complete combustion of methane, as you see here. This is an exothermic process and produces 890 kilojoules for every 1 mole of methane that is consumed. And as an example of other fuels, you can see that there are a variety of values that are associated with the combustion of things like elemental hydrogen or ethanol or methanol or even octane. So, and of course, these are all very, very important in our modern society in terms of various types of work that can be done with this energy. So, for example, we could talk about the fuel for your car, or possibly in the case of the space shuttle, we typically use elemental hydrogen as the fuel. Oftentimes you will find in various compilations of data, such as the CRC Handbook of Chemistry and Physics, a variety of these enthalpies of formations that have been measured under standard conditions. So, for example, the standard conditions are a situation where the reaction has been measured with a pressure of 1 atmosphere and at 25 degrees Celsius. So, again, the standard state is denoted as the superscript 0 just to the right of the H. In the case of the standard enthalpy change, all right, this would be delta H naught or delta H 0, depending upon how you would state that. So, it turns out that there are some things that are known as allotropes. Allotropes are substances that of the same element that it can exist in different forms, and so it turns out that diamond and graphite is a really good example of this. And so both are essentially made of carbon, and so in this case you would have a slightly different heat of formation for this. Typically an element would have a 0 delta H of formation, but it turns out that since carbon has these two allotropes, that one of them is graphite is the one that has the 0 for the heat of formation, whereas diamond has a non-zero value. So it turns out that the enthalpies of formation are typically referenced to the most stable form of the substance that we're talking about. And so under the given set of conditions, for example, the enthalpy of formation of steam, gaseous water, is shown here. We are making the water, 1 mole of the water, from its elements. So it will take 1 mole of elemental hydrogen and 1/2 mole of elemental oxygen to do this reaction, and it produces 241.8 kilojoules, which is an exothermic process. So likewise, we're always forming 1 mole of the product, and we're making the compound under standard conditions here. So in this case, if we're forming an element, if we were to form an element, then in its most stable form, then this would have a value of 0. So, for example, making elemental hydrogen from itself results in no net heat of reaction. Seen here is a tabulation of some of the enthalpies of formation for various substances that kind of bring out this point here. So, for example, elemental sodium, sodium itself in its most stable form is a solid, and therefore its heat of formation is 0. Whereas if you had sodium in the gas phase, you would actually have to put some energy into sodium in the solid state to get it to be in the gas phase. That's why the heat of formation of a gaseous sodium is a positive 107.5. Likewise, an ion, sodium cation, is an exothermic process in an aqueous solution, because this is energy that is given off when sodium loses an electron. And likewise, in terms of elemental carbon, graphite is the most stable form, whereas diamond, you actually have to put in a little bit of energy to get graphite to become diamond. And likewise, we have water in the gas phase versus water in the liquid phase. And of course, they have slightly different values because of the phase transition between those two states of matter. So, typically these enthalpies of formation can be found in some sort of tabulation. There is a table of heats of formation in the files folder for Canvas for this course. Typically, we can use these heats of formations to calculate the enthalpy of various reactions involving the compounds that are listed in these tables. And the general formula for us to be able to do that is if we were to take and sum together the heats of formations of the products multiplied by their stoichiometric ratio, the N in the balanced reaction, and then subtract away the sum of the heat formations of the reactants multiplied by their stoichiometric coefficient, then overall this would give us the heat of the reaction, as long as it's a balanced chemical reaction. Notice that in this equation, the capital Greek letter sigma means to sum together, and of course N is the number of moles from the balanced reaction. As an example of how to use this equation to calculate the enthalpy of a particular reaction, so in this case we have a question asking what is the standard enthalpy of the reaction for the reaction between N2O4 and elemental hydrogen, which requires 4 moles of H2 to produce elemental nitrogen, N2 plus 4 moles of water in the gas phase. So in this case then, our overall equation is the delta H is equal to the sum of the products minus the sum of the reactants. In this case, we can go to our tables and look up the enthalpy of formation of the N2O4, which is positive 9.16 kilojoules per mole. And for hydrogen, of course, that's an element in its most stable form in the gas phase, so that's going to be 0. And then for our products, we have N2, which is an element in its most stable form, so that's 0. And of course, gaseous water has an enthalpy of formation of negative 241.8 for 1 mole of the water. Now, if we then take and include the stoichiometric coefficients in our equation, the values of N from the balanced chemical reaction, and then we can go ahead and plug in our delta H values into this equation. And now we can take out our calculator and do all the math, and bringing all those numbers together gives us a value of negative 976.36 kilojoules, which then, if we deal with our sig figs, is negative 976.4 kilojoules for the reaction as you see it here under standard conditions. Likewise, we might have a slightly different problem where we know the enthalpy of the reaction, but we don't know the heat of formation of one of the either reactants or product. So, in this particular case, we have a bomb calorimeter that was used to measure the enthalpy of combustion of acetyl salicylic acid, also known as aspirin, and was determined to be negative 3,926.71 kilojoules per mole. So, and this is at standard conditions at 298.15 Kelvin. So, what is the enthalpy of formation of the aspirin, the acetyl salicylic acid? Well, in this particular case then, we need to determine the things that we can look up and the things we need to calculate. So the C9H8O4 is our acetyl salicylic acid. That's where we're going to try to figure out. The elemental oxygen, an element in its most stable form, is got a heat of formation of 0. The carbon dioxide, you can look up, and that's negative 393.5 kilojoules per mole. And the water is negative 285.8 kilojoules per mole. Now, in this case, then, we take our coefficients, our N values from the balanced reaction, and plug those in for the products minus the reactants. And then we can go ahead and plug in the delta H of formation values. And if we then do all of our math, we can come up with a value of solving for the acetyl salicylic acid. And if we combine all of our terms, we'll multiply the 9 times the negative 393.5, the 4 moles for the water times the 1154, and the 1 times the variable that we're going to solve for, and of course 11 times the O2, which is 0. We bring all these values together, and we are going to then have to rearrange the equation a little bit, solving for the delta H of formation of acetyl salicylic acid, and we ultimately come up with a value of negative 757.99 kilojoules with 3 sig figs is negative 758 kJs per mole for our heat of formation of aspirin.